Hello, everyone. Thank you for joining in. We'll wait for a couple of more minutes and then we'll begin with the session. All right, I'm going to begin with the session now. I will start with a quick introduction and then we will move on to the presentation. Is my screen visible?
Yes.
All right, thank you. Good evening, everyone, and welcome to the 9th Academy session exclusive for membership by Formula Bharat. Our speakers today are Siddhartha Dey, Siri Ajampur, and Ujjwal Chakru. They shall be presenting on the topic Design and Strategy Guidance for Formula Bharat participants as a part of the Membership by Formula Bharat initiative. A little about the speakers. Siddhartha Dey. Siddharth completed his BTech at SRM University, then went on to complete a Master of Science in Racing Engine Design at Oxford Brookes University. While a student, he was a member of two Formula student teams, Camber Racing and Oxford Brookes Racing. In his current role at Garrett Advancing Motion, Siddharth serves as a senior electric boosting powertrain system engineer. A little about Siri. Siri holds a master's degree in engineering design from Picompic University. In her student years, Siri participated in racing events for go-karts, all-terrain vehicles, and Formula student. She is currently employed by Scania R&D as a design engineer for instrument panel on trucks. In addition, she has been a design judge for Formula Bharat for over a year. A little about Ujjwal. Ujjwal completed his BE in mechanical engineering from NIE Mysore. In his student years, Ujjwal was a member of Force Ishwaku Racing and participated in FSEE events. He has been associated with LAM Research as a mechanical engineer since 2020. The content that will be covered during this workshop session. Over the course of 2 months, this membership workshop will be divided into 3 sessions. Here are the topics of the session. The last session that was done was Professional Approach to Formula Bharat. Today's session is Design and Strategy Guidance for Formula Bharat participants. And the next session, which will be held in December, would be Manufacturing Guidance for Formula Bharat participants. For young engineers, Formula Student is an incredible learning platform. Over the course of a full year, it requires multidisciplinary skills as well as an industry-like approach from start to finish. The workshop is directed at teams who are participating in Formula Student-like competitions for the first time. The aim is to inculcate a holistic perspective towards race vehicle engineering using principles of project management, product development, and vehicle engineering. In this session, participants will learn how to start up a Formula Bharat team, gather resources, set goals, and implement best practices to achieve them. Without further ado, we'll begin with the presentation. Ujjwal, over to you.
All right. Thank you, Anita. Hello, everyone. Good evening. Let me go ahead and share my screen and we can get going. I think it should be visible now.
Yes, your screen is visible.
Brilliant. Thank you. All right, everyone. Like I said, evening, and thank you for being here. So today we will be doing a slight deep dive into design for Formula Bharat and how do we trickle down from your competition targets to your component level targets, and also in the middle, how do we package in your system level design as well. So before we go into all of that, just a very brief into the whole the whole competition. I think this is something which we also talked about the last time, but again, just to give you a brief one more time, the main thing behind this competition is to get you guys do engineering designs through a vehicle prototype. And the reason we do a vehicle, to be honest, it's way more fun than say doing a fan design, right? It's not that fun anymore. So we ask you to do a car, which is more fun, and because it's a base car, it's a slightly more challenging thing to do. And then we benchmark your vehicle for some two kinds of events mainly. One are more dynamic, where you have to actually go and drive your vehicle through like a predefined track, and also a few others which are more towards, I would say, more theoretical in your designs and your B plans. And even like a very common theme in both these sub events is that it's all driven by your vehicle design, right? And finally, you do have the option to have like a battery driven or a CPV powertrain. So it's completely up to you as well. And then the whole event pattern. So towards your dynamics, so we have a few events. We have your acceleration, autocross, endurance, efficiency. So these are your more dominant events. This is happening on tracks. So you have to drive your vehicle. And then we do have a few tests as well. So first we have TI to see if your vehicle is even meeting the rule book. You have your tilt test, noise test, and then also your brake test for CV. And then on the other end of things, so first of all, we have the BED, where we check your whole vehicle design, and then we have the B plan and the costing report as well, where we just check your bombs and things like that. And then finally, while you are still developing the car throughout the whole season, we have a few submissions as well. We have your DSS, which is like a top level Excel sheet, which will have a few numbers about your vehicle. Let's say your vehicle weight distribution, size, engine, and all those things. And your SES, which is more towards your frame design, and a FMEA, which is only right now there for a battery driven vehicle. But yeah, if you are trying to do a better job with your even with your combustion vehicle, it'll be always good to have a FMEA for that as well. So this is the whole event, right? This is the way it will pan out. So the way I would say the best way to go about doing your vehicle design for Formula Bharat, right? So we have to dial down a few things before we go down into your vehicle design. First of all, what's your target of the whole event? Are you just trying to hit some lap times? Are you trying to get a certain amount of points or a certain rank, or do you have a weight target on your vehicle, right? Or just it also can be something very simple, like just having a car which is feasible, or even have a vehicle which will just go through your TI. It can be something very simple, or it even can be something very complex as well. It's totally up to you. So when you do choose to do a vehicle for Formula Bharat, it's totally up to you what your final targets will be, and then it's up to you the way you build your vehicle to actually hit those targets as well. And I would say one a good way to do is to have a top-down design process. first things first, just dial down your top level intent for the whole event. Okay, so this is the event. This is how many points we want, or let's say this is what rank we want. So this is your top tier goal, and then you come down to, let's say, sub event goals. So say if you want 500 points totally, it'll be 100 points, let's say, per dynamic event. So then you can break it down. So I mean, to have totally this many points, we have to have this much in my dynamics, and this much in my VD or my replan, and then based on those sub event goals, you come down to your vehicle targets. So to sort of have this much lap time in my autocross, we have to have the vehicle has to pull these many G's in X and these many in Y, and then we come down one more step. Okay, so sort of pull so many G's in X and this much in Y. Your drivetrain has to be generating this much torque, or your wings have to be dumping this much downforce, and then you come down one more level. Okay, so for your drivetrain to have this much torque, your intake has to have this much flow rate at this much delta P, right? And then finally you come down to your part level targets. So for your intake to be pulling so much flow rate, you have to have this much intake volume, and that's when you come down to actually doing your component design in CAD. So top level, the whole competition goals, and then piece by piece you come down to your part level goals. So it's very easy, I mean, to do it this way, top down. Bottom up, it's very difficult. I mean, you cannot say because I have this much intake volume, or say this much big wings, my vehicle will be in the top 2 or top 3. It will not work that way. And these all targets have to be very tangible. So 200cc kind of volume, 2 G's of G-force, this much downforce. So numbers have to be there. By just saying we'll have a best car, a fast car, good car, I mean, it's not very too tangible. It's very difficult to then try to work and build a vehicle that will actually hit those targets, right? So after this whole top down situation is dialed down fully, then we go into our system level design, because it's a full vehicle. We do have a few different subsystems. So we have your powertrain, which will just be generating power, to have your so that your vehicle will move. So that's one main system. Then you have your chassis, which is just having, it's like a big bracket which is holding the whole vehicle together. So you have your vehicle dynamics, which is your dampers, uprights, all of that, which will help your vehicle move on the track. And then you have your wiring systems, brakes, and your body and your wings as well. I mean, if you choose to have them. So these are very different kinds of systems, and they have to be brought together. And they have to be brought, first of all, to have the whole car built, and also they have to be developed towards a very common intent. I mean, it can't be that you are trying to lose weight with your chassis, but then so you have a very big engine. So it all has to be in sync, so that if I can just go back here to hit your top level goal as well. So it has to be all in sync, right? So this is your pretty much how you have your different systems, your top level goals, and then the way we should have our top level targets dialed down to hit those. I think I'll take a pause here before we move into system integration, and Siddhartha, you can maybe pick it from here.
Yeah, thanks Ujjwal. So like already discussed before, you have to come down from your top level targets, vehicle targets, competition targets, and then make those targets translate into your inputs for your system integration design. But then what is basically system integration? How do you define system integration? Is because, okay, so you have an overall vehicle over here, let's say in the middle of your in your vehicle design, and then you have, for example, a chassis, subsystem or a sub team, and then you have body panel, drivetrain, aerodynamics, powertrain, and other things. What is really important is, we all know a vehicle is made out of these subgroups, and they need to come together to for the vehicle to be a complete thing. But what is really what we say system integration is when each and every subsystem is also talking to each other. Means the drivetrain is talking to the body panel team. So let's say these are sub teams in your team, and one team needs to talk to another, one subsystem design needs to talk to another. So if maybe usually you go to the next slide, you see that chassis cannot be an individual team, sub team, and make their own targets and make their own design. If that doesn't fit to the brake subsystem, or if that doesn't fit to the body panel subsystem, it's not going to work over there. Similarly, it has to also, for example, the brakes have to go along with electrical and electronics. For example, you are putting some kind of brake pressure sensors or brake pedal position sensors. So you need to communicate amongst each other and define what kind of design or targets you would like to have over there. And then again, you go to powertrain, electrical, electronics, aerodynamics, they all have to work together. Otherwise, your vehicle is going to be like just a collection of different designs which don't integrate properly, which don't follow the main goal or the main target of your team for the competition. So that is why it's really important if you if you all have one target and then divide that into subsystem targets and then work towards this one common goal. And important is you talk to each other. So subsystem drivetrain is talking to subsystem aerodynamics, and then again aerodynamics is talking to a subsystem powertrain, and so on. Otherwise, you all will make a chassis which is, for example, too heavy. Powertrain is too light, brakes are not powerful enough for the vehicle to stop itself. Body panels are, let's say, too small, too close to the exhaust manifold, for example, getting hot and burnt out. The drive ratio is completely off. If the target was to go acceleration from 0 to 75 meters in 5 seconds, and if your drivetrain ratio is totally off, you will reach that in 6 seconds or 10 seconds. So what we want to say over here is basically that you have to bring everything together and remember what the overall target is of the team. And then if you go to the next slide, you will see over here is a basic layout of how your component level design should be. So by component level design, what we are saying here is if you just take the example of an upright or a drive shaft or just the sprocket of your drivetrain, so just one single component, then you have to decide. So for example, if you are the design engineer or you are, let's say, leading the team of drivetrain who is making the sprocket, you have to ask yourself, what is the problem? What is the problem statement over here? What are the requirements and specifications? And then you have to go on to the next phase of, okay, so this is my boundary condition. What is available or what is the state of the art? What is available in the market? Do we have to make something new? Or if it is a problem that you are facing in testing, so why is this problem happening? Why, from which component it might be coming? What does the data say over there? So this is basically the research you have to do in this phase before you move on to the other one, where you are basically laying out all your solutions, your possible solutions. It really doesn't matter if you have 5 solutions or 10 solutions, what is important is for each and every one of them to be assessed properly. You need to put in how much time you need for each solution, what kind of money or resources you need for each and every solution, and what quality of work you can provide in the given amount of time. So 5 solutions, for example, money, time needed, resources needed, and at what level or maturity level you will have the solution at the end. So this is what you should do. And then again, the next phase where you have the planning. So you take 5 solutions and then you say, okay, solution number 3 is my prime path. This is what I want to do because it is according to the timing. It is according to the budget that we have, and it will also fulfill the maturity of the design or quality of work. So that is where planning phase comes into all of this. And then create is where you basically do your simulation, your design, your manufacturing and assembly, which we all know we are doing. But then comes testing, validation, which many of us kind of take for granted, because we are always stuck into design and simulate, and we keep on designing and simulating forever. So what you have to do is at some point stop, design, simulate, make it validation and evaluation. What does evaluation and validation means? That okay, you have a design, you have a solution, you think it will work, but does it really work? So you have to do testing, collect data with the help of different sensors, with the help of, if it's on an engine dyno, chassis dyno, you are testing a brake, what is the brake pressure, pedal force, those kind of things. Put it into your calculation back and then check, okay, is my calculation correct? Is the input of the calculation which I put in few steps ahead, is it correct or not? So that is what you should do. And then the last is, if everything fits what your intention was at the beginning, that's well and good, but most of the time it happens that it is 70% or 80% of what you want. So the rest 20% needs to be still improved. So then you go back, change the design, optimize, test, and do it again till you reach your final satisfaction level over there. So this is a basic layout process of how you can design a component. This is a method available everywhere. You will see it's a really general way of working. You can remove a few steps, you can add in a few steps if you want. But the basic point that you see on the bottom of the presentation is you have to think, you have to make something, and then you have to break it and then go back. So this process keeps on happening. It's the same in industry as well. You think about something, then you have to make it, and then while you're testing, you of course break it, because it's always an iterative process, and then you go back and keep on doing till you have your final design. Good. So I think that is all from my side, and then I hand it over to Siri, who will take you through the other slides. Thank you.
Yes, I will start by sharing my screen. Or if you already have it, then.
No, I just stopped sharing, sorry.
That's okay. That's okay, I can do it. You can see the screen. Okay, so till now we spoke about the system design and the component design once you have all the system parameters ready and so on. And now we can talk about how to understand that your system has reached your design goal. So let's say that your design goal from the beginning was to have a weight target of, let's say, 200 kilos, for example. And then you've designed your frame, you have your engine, and then you have all the other subsystems like brakes and suspensions and so on. And now you don't know if you have attained your goal or not. So one method to understand if you have reached your design goal is first through optimization. Then we have simulations, and then we also have simple calculations, which will tell you, which will at least give you an idea whether you have reached your goal or not. For example, if we take the weight goal of 200 kilos for the entire vehicle, then you already have a very visible target validation. If your total weight of the vehicle is 200, and then if your engine is already let's say 70 kilos, you've used up almost half of your weight already. So then you have very little weight allocated for frame, and then the brakes, and then the suspension and the tires and so on. So then if you break it down and say that, let's say your frame weight is around 30 kilos, then you only have 30 kilos to work. And in those 30 kilos of metal, you have to make sure that it is also safe for the driver in case of an impact. So that is where the FEA comes in, or any sort of simulation, because you cannot really make a frame and then see if it crashes or if it's safe or not. So this is a method to iterate and understand if you've reached your design goal and if you've reached, in this case, your weight targets. So let's say you have 30 kilos as your weight target, and that you need to simulate some crash scenarios and already the impact attenuator calculations and so on. So how do you make sure that you're attaining your safety or the stiffness that you require in 30 kilos is what FEA is all about. And that is why you're doing these simulations. The most important ingredient for a simulation is the real case scenario. So if you develop the boundary conditions as close to the reality as possible, you will get a very realistic result. But for beginner teams, we understand that it's both lack of actual test results or the lack of experience to have perfect boundary conditions in order to have realistic results. So what do you do then if you don't have a good boundary condition? The first thing is to have practical scenarios. For example, if you have to test a crash scenario, the first one is already given for you. The impact attenuator boundary condition is already in the rule book, so use that directly. And then for side impacts, understand what sort of crash scenarios can actually come up in a Formula Bharat perspective. For example, there would be very little chance of side impact from a complete vehicle crashing into the side of another moving vehicle. It would be more likely that the two vehicles graze side panels next to each other. So probably you could take inspiration from practical track scenarios and set up your case studies accordingly. So there is probably no need to have a worst case scenario where an entire vehicle is having a head-on collision with another vehicle. So you could use such practical information already available to you. That's the first thing. And secondly, if you have the track data already available to you, and also the track data from previous years, you could use the lap times as an example to simulate your powertrain or to simulate aerodynamics as well. And then let's say that most cars who stood, let's say top 3, recorded 2 minutes per lap. That's just an example. So you have to break down this goal that you've set. Okay, the last teams have achieved 1 lap in 2 minutes, and we're trying to achieve something similar, let's say 2.5 minutes since we're a beginner team. And then you have to sort of understand which systems will actually contribute to this particular lap time, and then make FEA accordingly. So if you say the top speed we need to achieve is 80 km/h for this particular lap time, and then you try to optimize your intake valve so that you get 80 kmph in the time that you have opted for. And for mostly flow-related simulations, it is better to use transient models instead of steady state, so that you have much more realistic data to analyze. For example, your intake simulations, the aerodynamic simulations, thermal simulations can all be transient, so that you have more working data. And about meshing, you can properly choose to understand which areas in the car are more critical. For example, the most critical parts usually teams have problems with are the hub, the tire area, the upright area where the tires are mounted, the frontal impact area, and mostly the mounts where there are heavy devices placed. For example, the engine mounts, which take a lot of noise and vibration, and also the suspension mounts and so on. So understand already which areas are more critical in the car, and then try to refine the mesh in those areas and work with it. And also, once you have all the test results, it is very hard to understand what exactly the images in the simulation software are showing. For example, if you use ANSYS or even SolidWorks simulation, you finally end up with an image that looks blue, green, and red, and then you can already make out from the picture that red areas are critical. But you should also use your common sense to understand which areas are critical in practical and which areas are showing red in the design, so that you can go back and try and analyze which areas are critical and which areas are just anomalies from the software and the way that you've modeled it and so on. Because for the first time, using the software is also hard. And you can also get a lot of wrong models because your CAD is not exactly optimized for the software that you're trying to simulate in and so on. So for the beginner team, it would be really nice if you could understand the physics instead of just looking at very minute details of, let's say, stress or displacement and so on. And how is the data being archived? It's very important that you try a lot of designs, not make like one design and alter it very minutely, but make very different designs and compare the values. You may not get good values at first. You might not even get useful values at first, but understand the delta between the designs and always try to archive it with the boundary conditions. Change the boundary conditions, change the designs, and see how much of delta you achieve in every step, and understand which area is looking better in which design. So that would really help. And then we also have some guidelines on how to iterate. How many iterations do you think would be good enough? It's hard to have a stop sign and to know where exactly you need to stop these iterations. For example, it's always better to have fixed parameters that you're looking for. For example, in this case, we have the weight target of 200 kilos, and let's say the frame weight is 30 kilos. So if you've achieved your safe areas, for example, if it's the cockpit, if the stresses are not reaching the cockpit, even when you have your worst boundary condition, and it is achievable within 30 kilos, it's good enough. So have parameters according to your design goals, and once those parameters achieve those targets, you need to stop the iterations. And then once you've had simulations in every subsystem, you should try and integrate all of them and try and make sense of it. If your engine weight is 70 kilos and if your frame weight is 30 kilos, then for the powertrain, there is no need to use a worst case scenario of, let's say, 300 kilos. It's easier to use the targets that you've set for your own car and use it as a criteria for this next subsystem. A lot of teams, they use like the worst case scenario for every subsystem. That is not required because then you will over-engineer every subsystem. That is one way to integrate systems as well, to use the same boundary conditions that you have used for other systems. Then this is more or less how you decide that the targets you've set are achieved, and this is how you would optimize. And most importantly, before getting into the details, you can make a rough calculation, understand which parameters are the most important for your main goal. If it's the weight, then maybe you can divide every subsystem and every component and estimate weights so that you have the targets already and use that as a boundary condition. And if it's lap times, use this lap time in every subsystem. For example, this should be your drag coefficient, or this should be your top speed, and this should be your gear ratio, and use those as boundary conditions. So that's how you iterate and also stop iterating. Then we have, how do you use these? And all these simulations and optimization will help you until the virtuals or the design event. And then when you start manufacturing, it would be a huge difference in the results and also in terms of engineering. Because as beginner teams, you wouldn't have access to the real-time data, and you're quite far away from the reality as it is. So why do you have to use these simulations? It's only for getting the clue of how to design, and the final validation should always be in terms of a prototype. If you are not confident in building an entire vehicle, you can probably choose to make smaller subsystems. Maybe you can just test the engine and the cooling. Maybe you can just test the ergonomics as one system, and maybe just the aerodynamics as another system, and then probably integrate all of them together. And you should probably allow a lot of time for testing, maybe 1.5 times more time for testing than manufacturing, because as beginner teams, it's most important to understand what went wrong and to have time to correct it. And try to understand what sort of sensors you would use, where you would place the sensors to have good amount of data, and also how to repair your designs and components once it's already fed into the vehicle. The systems, like I said, can also be tested in isolation and then be integrated. And what if something fails during testing? Always have spare parts, and always have a good archive of all your boundary conditions and simulations, so that you can compare your simulation to a real-time test. And this is also a method of understanding if you have reached your design goal or not. And then we lastly have packaging. I think this is one of the most important things you need to do before you start building a vehicle. And this is to understand how all the parts are mounted and how all the parts fit into the perimeter of a vehicle. Most teams will not have a full 3D model of the vehicle. You might have a frame, you might have a box for an engine, or you might have brakes, but not the brake lines. You might have battery and so on, but not the wiring. So it's important to understand the connections between different devices on the vehicle. For example, if you have four brakes, then you will also have 4 cables coming in for a brake fluid piping coming in from all 4 discs, and then you'll have a master cylinder. So you can imagine it in 3D space, but when you have a vehicle to assemble, you need to understand where to mount these smaller devices and smaller parts. And also, for example, the kill switch and the safety devices. How would you mount it? You would have only thought about assembling the engine. Okay, the engine sits at the rear and the gearbox sits in next to the engine and so on. But you should also have space left to mount the firewall and the kill switch and so on. And we've seen many teams which have seatbelt mounts, which are kind of made last minute. So it just sticks from the behind and it's not even safe. And it also won't get you through the technical inspection. So it's better to understand how to mount all the subsystems in a good way so that your car looks neat and has no problem clearing the technical inspection. And also the most important things are the fuel tank as well. If there is no proper fireproofing and there is no proper leak proofing for the fuel tank, it would be probably a ticking time bomb, because it's easy to say, okay, we will put the fuel tank here, but the little details that you have to take care of, maybe clearances. If there is a gearbox which has moving components and you put the fuel tank very close to it, maybe the particle stuck in the gearbox can damage the fuel tank and it might leak. So you need to have some sort of idea of the layout of the entire vehicle so that you have enough clearances between the moving parts, the critical components like fuel tanks, the piping, and so on. And then most importantly, to have tolerancing, because this is a student-made car and you would probably not be using industry level machining, or if you try to make it by hand, if it's grinding or notching or welding done by hand, then the tolerances are way off. So you need to keep in mind that in CAD, if you have, let's say, camber angle of, let's say, 0.5 degrees, which we've seen in many design spreadsheets, it's very difficult to put 0.5 degrees in reality. So understand which components need machining, which components need good tolerancing. For example, if you're powder coating all your frame parts, and if you have a lot of holes on it, the fasteners may not even fit into the holes because you have not accounted for the powder tolerance. So understand what sort of precision you can achieve with the machining that you have available, and understand how much clearance and tolerances you need for it. So I think this is one of the most important things that many people fail to consider. You need to have a good 3D model of the vehicle where every part fits well with tolerances, and to have a good mounting practice for each small device as well. So that's all that we had planned, and we are done with the presentation, and we are open for questions.
Thank you for that presentation, Siddharth, Ujjwal, and Siri. Students, if you all do have any questions, please feel free to unmute yourselves and ask the questions, or if you all want to type in the question in the chat box, please do so.
Feel free to ask anything. Don't worry how intelligent or stupid the question might be. I think every question is a good one.
Exactly.
I'm sure that at least there will be some questions and or doubts that you'll have regarding what was presented. So please feel free to unmute yourselves and ask the question, or else just type the question in the chat box.
How do you decide what target parameters to set to start iterating designs without prior experience? Good one. Who wants to take it?
I can take it, I guess, because this is a pretty interesting question, right? So let's say you've never done a vehicle before. This is your first vehicle. So how do you define targets? Pretty good, right? Because you don't have any baselines at this point. So I would say, as a very ballpark estimate of things, just go to the Formula Bharat website, right, and see their results from last year. See what kind of lap times are teams actually hitting up, right? So that's what okay, for this dynamic event, we have to hit this much lap time. So it gives you some baseline, right? Target it from that level first, and then trickle down to, let's say, your system level designs and so forth. Does that help you? Does that make sense?
If I can add to that. So for example, if you have if you're taking an upright, let's say front or rear, doesn't matter. So if you're taking upright and if you are doing some kind of FEA analysis on it, so you should already by now have all your forces coming into the upright through your wishbones, through your wheels, through your brake calipers, and all of those things. And you are now checking, let's say the first design of your upright weighs 1.5 kilograms, and you have a factor of safety of 1.5 as your target parameter. And with 1.5 weight and all the forces you have given, you see a factor of safety 3. After your FEA calculation. So what I would do is, again, then you go back, you reduce your weight, you make some holes, some cutouts into your 3D model, and then you come back and then you say, okay, factor of safety is 2, and then you do it till you have 1.5 factor of safety. But then you can say, how do you say a 1.5 factor of safety is a good one for an upright? So all of this is really based on experimental values or experimental, let's say, testing that each and every one does. For one team, a factor of safety 1.5 can be a good enough factor of safety, depends on the material, depends on a lot of things of that component. So it is like Ujjwal was saying, you can do your own research, and on the internet, there's a lot of resources available, and you can really easily find ballpark area of your final targets. And then once you are at this ballpark area in your iteration, in your CAD, in your CAE, I think that is when you are good to stop and then move on to the next one.
Yeah, and I would also like to add, for the target parameters, you can probably, as a beginner team, try to start with the dimension of the entire vehicle. Let's say the rear width, the track width and the wheelbase. When you have these two parameters, you get the turning radius. And when you have the turning radius, you can understand the type of the track that the competition is going to be held at. And then you can probably analyze what lap times, as Ujjwal said, what lap times the previous teams have done. So try to compare your turning ratio and try to compare the lap times and see if you can make some sort of equation that suits your weight targets as well. And understand what torque, what engine torque is required for that, and then kind of work backwards from one particular parameter. Probably if you take weight as an important parameter, then, and let's say that you're not going to make every single component in this car. For example, the brakes and the brake pad. Let's say you're not going to manufacture it yourself. Then if you assign a particular weight, understand for that weight, which brake pads and brake discs are available in the market, and see what parameters they have, what sort of brake force they can give you, and compare that brake force with the torque that you need to have and the lap time that you need to have. So have a main goal and then have some parameters associated to the goal, and then try to see what works for you the best. Even with the engine, if you have a weight of, let's say, a very ambitious weight of 150 kilos, then you cannot use an engine which already weighs 80 kilos. So some things which are simple, you can decide already. Some, for example, even the budget. If you have a budget of, I don't know, just very vaguely, 1 lakh rupee, and you cannot select brakes which are too heavy or too costly. If you feel that having technical targets is way too difficult to work with, have more realistic and more tangible targets: cost, weight, top speed, dimensions of the vehicle, maybe turning radius, and so on. That would also help in the beginning, at least.
The
Thank
next
you for
question.
answering that question. Yeah, Siddharth, you want to go ahead? Please go ahead.
Yeah, I was just saying that there's another question in the
Yes.
chat, saying that considering the package constraints, what could be the tolerances if a team has not enough machining tools or resources? So if I just can put some remarks over there, there are some books available that you can buy, which are giving you standard mechanical engineering tolerances or standard tolerances for machining purposes. What you can do is, for example, you go outside to any supplier who is machining a drive shaft or a sprocket or a bracket or a mount for you out of aluminium, out of stainless steel. So you make the 3D model and then you make the 2D drawing of this for the machinists. And on this 2D drawing, you have to specify if they should use the standard tolerances according to the machine, according to whatever standard is there, or if they should use the tolerances that you have specified on the drawing. So this is what is important over here. And for standard tolerances, for example, I can put in the chat, there is a very good book that you can follow. I will put it in the chat. So this is, this is just an example. You can of course have other books as well. So for example, you want to drill a hole of 50 millimeters in some part, and then you have to say that, okay, the hole should be 50 millimeters nominal dimension, and then you have to say if it is a plus minus of 0.5 millimeters or if it's a plus minus of 0.1 millimeter. And this really comes from the supplier who is doing it and how much of a good fit you want inside this hole of 50 millimeters. If you want a loose fit, you go for a higher tolerance. If you want a tighter fit, you go for a tighter tolerance over there. So all of this really comes down to basic mechanical engineering design 101, CAD engineering and 2D design. And then once you have all of this, go to the supplier, show the drawing. Okay, we want here so much tolerance, we want here so much tolerances. And once you have all of this information and knowledge, your packaging will be really accurate, and you will see once you make your final vehicle that what you have done in 3D model is actually matching your hardware, your reality over there. It will not be like, okay, you made a wishbone with a hole for mounting it with the M8 bolt, but once you have the hardware in your hand and you put the M8 bolt inside, you will see, oh, it's moving, it's loose. Why does this happen? Why is it loose? And why do you then have to put a washer inside it? Because you have not calculated for the tolerances of machining, of manufacturing. If you do it properly, then once you take a wishbone with a hole for M8, you put an M8 bolt inside, it will be a perfect fit over there. You won't need any washers. It will not make any sound when you're driving the car. So these are things that you have to take into account.
Thank you for that reply, Siddharth.
Also, a good practice would be to have some sort of jig and fixture for at least the welding of the frame, and the most critical thing is the mounting of the uprights. So if you have a proper, if you can use some sort of precision just for the most critical component, that would also help you achieve a good tolerance in general.
Yeah, I think, for example, if you are making a space frame chassis, or if it's just a simple wishbone, it's very simple that you take a piece. So for example, a wishbone, you take a piece of wood or any flat surface, then you print out in a sheet of paper the 2D drawing in 1:1 scale. Put it on that piece of wood, put some nails, put the rods, or if you're welding, put the rods over there, and then you weld it. But what is really important over here is when you are putting the piece of paper with the drawing, when you're putting your nails, for example, or anything to fix the two rods, wishbone arms, even when you are putting the nail inside, you are welding, you always have to make sure that none of this is moving, because after you weld, it kinds of it wants to cool down, and then if your nails are not properly hammered into the wood, they can come off or they can bend, and then your wishbone, after it cools down, is let's say a little bit off than what you had imagined in 3D. So even jigs and fixes are probably a really good idea of putting tolerances into place, but you also have to be careful over there.
Do we have any more questions? If you do have any questions.
For more, right? Out of hope
Sorry.
for more Q&A. I mean, it's the design session. I mean, but hope for more. Yeah, looks like that's about it.
Ujjwal, were you expecting more questions?
Oh yeah. For design, at least. I mean, people always like, how do we do this? How do we do that? But it's like, it's all taken care of. So it is always, good, but I don't know.
Guys, please don't feel shy to ask your
not at all.
questions here. Yes, please go ahead and
fire away.
feel free to ask your questions. Like Siddharth mentioned, don't feel that your question is going to be stupid or, silly. Every question is important here, and we are here to help you out. So please ask your questions.
And don't, type it out and wait. Just unmute and go ahead.
We'll wait for a couple of more minutes to see if we have any more questions, or else we'll end the session. There is a question.
Hey, how detailed should we be able to make? It's a pretty good one again. I mean, this guy is asking some, good stuff right there. So I think I can maybe, begin on this one. CAD representation, right? I mean, it should be at least, detailed enough, the very bare bones, right? Have your chassis at least with your suspension, with your powertrain, brakes, seat, so that at least the big things are taken care of. That first of all, at least that your templates will pass, right? At least that. But if you have time, also do your wiring, your cabling, your plumbing, all of that as well, because you might think that, hey, I mean, what's the point of me doing my wiring in my chassis, right? But it will really help you if you are trying to build your firewall. It's not a waste at all. So, and it's to be honest, it's a very good way of doing your vehicle design. So you should have everything in CAD. Ideally, the whole thing has to be in CAD, even your fasteners. right fasteners, right names, right numbers, everything, so that worst case something goes bad, you can go and check what's actually happened. And for some bonus points, if you bring a full-blown CAD into a BD event, I mean, it's amazing, to be honest. So yeah, you should have that.
Thank you for answering that question, Ujjwal. There's another question that's coming.
Yeah, I'll just quickly put one more point over there. So if you have your CAD as detailed as possible, at the end of the day, what you can see is, for example, if you just measure the chassis of your 3D model, and if you measure the chassis in reality, they should match. There cannot be anything going wrong over there. If you are making the whole brake assembly, each and every washer, nut, bolt, hose, brake hose, everything should be there how it is in reality, and it really makes a lot of difference. If you don't have a detailed CAD model, you cannot really make your vehicle compact or package everything properly if you don't have each and every model inside your CAD. So the other question was, could you elaborate more on data interpretation?
I have another point on the same CAD practice. It's more about CAD practice than the tolerance. It's very good practice to create a first space model of your car. Don't start with the frame. Start with just boxes. Make one box for the entire car. Make another box for all the body works. Make a box for the engine, make a box for the seat, and make sure that these boxes or whatever have some tolerance for in them. For example, 5 millimeter between the other parts. If it's a moving part, maybe keep 20 millimeters. Make so have your dimension of the car. Let's say it's 80, to give a very big example, 80 by 100 into 80, let's say. So have that box and have a market survey of the most biggest parts that you have, and then make these spaces for each system. Then try and fit in the devices in those places. Then you will have a good layout management or layout design. Many teams start with directly the frame and then they just drop components on it. Don't do that. First, make spaces for every component, then mount everything, and then try to understand the routing and the mounting. That would be a good CAD practice. And this is maybe more away from our topic, but having a good CAD is also extremely important. If you have a corrupt CAD, then it's very difficult to change things at the end. So have good CAD, and then have a CAD where you can move systems and still not make it corrupt. Because if many teams open their CAD model, most of it is red, and you cannot change one single thing without the entire CAD getting affected. So I think that's super important to have your CAD clean.
Yeah, I think the constraints are really important over here. The assembly constraints you have.
Yeah. So yeah, now we have a few guys asking questions, and I think I want to answer the testing one first before I talk about the data gathering, because I think it's it'll make more sense that way. Yeah, essential data while testing the vehicles. So I mean, when you say very essential, I would say at least log your engine data, engine RPMs, ideally at least engine temperatures, because engine temperatures can be of a big issue at times. Engine RPM, engine temperatures, your vehicle, how fast is your vehicle moving, G forces, ideally. Oh, for an EV, now you just flip the whole damn thing around. Okay. All right, so no engine temperatures for you. All right, so we still, and I think so you can do your, okay, now let me think again. So yeah, same G forces, vehicle speed at least, your BMS temperatures, I guess, right? For motor temperatures, again, if it's getting too hot, I think that's the very basic. I would at least have that, so that so that you can have some idea of how how fast is your vehicle, how many loads you have, and once you build on this, then you can do the more detailed things like your damper travel, or your or your what do you say column
Yes.
angles and
Yes, steering angle.
throttles, yeah, all of that, right? Yeah, this is, I think, basics at least.
Yeah.
Just this stuff.
Yeah, I think the basics should really be for an electric vehicle, like Ujjwal was saying, is so I don't know if the configuration is you have an electric motor to a gearbox, or if you have individual electric motors in individual hubs. But any electric motor you have, you should measure the temperature of the motors, how hot they are getting, what is the water flow, because if it's a water cooled electric motor, you should know the water flow, water temperature over there. And then the speed of those motors. So you can either measure the speed of the motor shaft, the reduction values, and then of course, because of the reduction values which are known, you can calculate the electric motor speed over there. But this is the mechanical side. Okay, if you want to now know electronic side, what you can measure: the current, the AC current, the DC current, your voltage levels over there, at what frequency you're changing. So these are things that you can really easily take from your electric motor controller. Shouldn't be that big of a problem. And then these are the basics, because if you don't know the G level speed of your vehicle, if you don't know how fast or how slow you're going, anything that you do later on cannot be calculated properly. Damper travel is good to have. Steering angle is good to have. Of course, if you want to be such detail, you can always put that over there. Then once you're braking, what is the amount of force the driver is putting on the brake pedal, and what is at the end the brake pressure. So these are things that you can also measure. But again, these are, let's say, the one level higher, and not the very basic data that you would like to have.
Exactly. And also, right, while testing, your data logging frequency, very important. If you have damper travel data as, I don't know, 2 hertz, it's waste. Have to have it at a very high sampling frequency. Again, dependent on what data you actually trying to log as well. So it's highly determined by that.
Yeah. And then again, you will of course have battery temperature, battery state of charge, and all those kind of details over there. Yeah. Could you then I don't know if we can go to the next one. Could you elaborate more on data interpretation? Where do teams go wrong on that front? Yeah, maybe Ujjwal, if you want to start.
Yeah, I want to begin this one. So see, data interpretation, right? It's a function of your data first of all. So let's say a very simple data point. So you have your engine temperature data point, and at the same time, you have your engine water temperature data. If you see that, so you have a very high engine temperature data, but there is no temperature data on your water. That implies that it's boiled off, right? So where teams would first of all go wrong is that they have very limited data points. First of all, they'll have, let's say, only your battery voltages. So you would know that, hey, my engine is not firing due to having low battery voltage. But because you don't have any other data, you never know if your plug is even firing or not, right? So first of all, try to have more data, rightly sample data as well. And I think that's what, like I was saying, teams go wrong when they don't have enough data. They have, teams very rarely have good data at all. So I would say, try to have very reliable data first of all, and then try to segregate what is the real phenomenon happening over there, and then what's just extra noise, right? Does that help?
Yeah, and I think what I can also add over here is, for example, if you are, even if we consider data in simulation, okay, not even going to the testing phase, even if you look at the data in simulation. So for example, you are doing vehicle dynamics simulation, or you're doing your powertrain simulation in GT Power or AVL software over there. It's very easy to, click on each and every option to gather so much of data and so much graph and colors. It's very easy to do that in software. But then you really have to understand, okay, which data is affecting which other data, what is connected to what, and what really makes sense. Because there's one thing of getting a lot of data, and another thing is to making sense of all the data and how they're connected to each other. So you basically have to find out, okay, so for example, if I have, let's say if I have, I'll take an example of an electric motor over here, electric vehicle with an electric motor. You are checking in simulation, how hot is my electric motor getting when I am at, let's say 60 kilometers an hour vehicle speed. And then you say that, okay, my electric motor is getting to 100 degrees Celsius. But then you have to see why it is getting to 100 degrees Celsius. Is your water, what is with your water temperature? Is your water temperature still constant to whatever you had estimated, or is the water temperature also going higher? Because the faster you are going, you also have to make sure that you are cooling your radiators properly for the water cooling. And if that water temperature is going higher because of bad radiator cooling, then your electric motor temperature will of course go higher, because the water inlet is not anymore at 25, for example. Now it is at 40 degrees Celsius. So things like this. So you have to always have a global picture of the system or the complete system. Which data is affecting what? And you, to be honest, you have to question each and every data that you see. You cannot say, okay, this graph is going higher, this graph is going down, this curve is like this. Okay, so maybe it is no. Question each and everything, why, what is happening over there. So I think that is, in short, that is what I would answer to that question.
Yeah, and maybe if you have access to softwares like Mode Frontier, which is multidisciplinary optimization softwares, then there is a built-in program which allows you to calculate the sensitivity analysis. So you can read up about sensitivity analysis. It's basically a mathematical program which you can do in an Excel sheet as well. You can try and add the most important parameters like the speed, if it's for an EV, maybe range, weight, aerodynamics parameters, and so on. And you anyways have access to all the equations. I think I feel that is what the beginner teams are best at. You easily get into the details, and I think it for you it is maybe easier to work with equations. So try putting all those equations into a good Excel sheet and then perform a sensitivity analysis. I think there are some templates in MATLAB as well which you can use. So sensitivity analysis will tell you which parameters affect which other parameters. For example, will the braking force affect drag? Or will the drag affect braking force? Will the drag affect top speed? Or will the CG affect CG position affect brakes, and so on? So read up about that and try and see if you can get hold of a student version of maybe software like Mode Frontier or any other multidisciplinary optimization software as well.
Yeah, and worst case, if you don't have that, the software as well, even MATLAB can do it, I guess. I mean, it'll take more time, but I think it should be able to figure it out.
All right. Thank you for those questions and the answers as well, speakers. We will end the session now. Before we end the session, I just want to check again one last time if you all do have any questions, please put it down out here. If not, then we can go ahead and end the session. All right, then we will end the session. And I would like to thank our speakers once again for the session this evening. We appreciate your time and commitment towards sharing your experience and expertise with the participants. Thank you to all the members for joining us. We hope you found the session enlightening. Have a good evening, everyone, and see you all at the next session next month. Thank you.
Thank you.
Thank you. Thank you.
Thank
everyone.
you.
Have a nice day.
Bye.